In 3.7b, we're going to do optimization problems, but this time more complex problems that require a calculator. In the first problem, doing with me number 1A, says we have two posts, one that's 12 feet high, the other one that's 28 feet high, and they stand 30 feet apart. I'm going to go ahead and start off with a picture with that information. So I have a post that's 12 feet high. I have another post that's 28 feet high, and they are 30 feet apart. They are to be stayed by two wires attached to a single stake running from ground level to the top of each post. Something kind of like this. So the stake is down here. There's wires running up to the top of each post. It says, where should the stake be placed to use the least amount of wire? Where should the stake be placed to use the least amount of wire? So I need to figure out, where do I want to put that stake? So can I call this distance x? If the whole thing is 30, and this little distance is x, well, this distance over here I can call 30 minus x. You could have done it, flip-flop those, and done it either way, and then you would just have to label your answer different. Okay, either way though, you get the same answer. It's asking us to figure out where the distance is that I have to place the stake. So I want to ultimately find x. But it also wants me to use the least amount of wire. So my primary equation, the equation that I want to optimize, would be the length of the wire. So can I call that W for length of the wire? Okay. And my wire is this length and this length combined. So if I call them Y and Z, then my length of my wire would be Y plus Z. And that's the equation that I want to optimize. Okay? But I have Y's and Z's in that equation that I need to somehow come up with a secondary equation that includes the same variable. So if you look at the picture, we have two triangles, and they are right triangles. So I know Pythagorean theorem on each of those little triangles. So on the left triangle, I'm going to use Pythagorean theorem, a squared plus b squared equals c squared, and solve it for y. So I end up getting the equation y equals 12 squared plus x squared. Simplifying that down, we get y equals the square root of 144 plus x squared, right? A squared plus b squared equals c squared, and then getting rid of the square by square rooting. So I have an equation that's y. Now let's do an equation for z. So I'm going to do the same type of thing, this time with the right side triangle. A squared plus b squared equals c squared. So z equals 28 squared plus 30 minus x squared. If you FOIL that out, combine like terms, you should end up getting z equals the square root of x squared minus 60x plus 1,684. So there's my equation, my secondary equation with z in it. So now I should be able to take my length of my wire equation, the equation that I want to optimize, and instead of y, I can plug in my square root of 144 plus x squared, plus, instead of z, I can plug in my x squared minus 60x plus 1,684, and then optimize that equation. Now, as you can see, it's going to be kind of difficult if you try to do that by hand, so this is where we're going to use our calculator. You're going to enter this in to your y1, just like it is here, making sure that you probably put parentheses around the inside values, so your calculator knows what part is underneath each radical. When you graph it, you're probably not going to be able to see it if it's in a standard window. So you need to either zoom out or fix your window so that you can see it. You might want to try some numbers that'll give you the best picture. But just to help you out on this one, the window that I picked an x minimum value of -5. I picked an x maximum value of 31, and I went up by 1. The y minimum value I picked as -5, and the y maximum value I picked as 60. I went up by 1. So this window should help you see not only the original graph, but if you turn on your derivative, your y3, it should help you see both the derivative and the original. Okay, so if I want to optimize the length of my wire, I want to find the derivative of my W function. And so using my y3, my derivative, I want to figure out where it equals 0. Okay, so looking at the x-axis, where does it cross the x? I use my second trace zeros, do my left bound and my right bound, and figure out where my derivative equals 0. Okay, so using the second trace zeros, you should get that my critical values are at x equals 9. Okay, so looking at my picture, I know that it needs to be 9 feet away from the 12-foot pole. But remember, we not only want to check our critical numbers, we want to check our endpoints, or if there are feasible domain restrictions. Okay, so looking back at my picture, I need to figure out what x values can't be, what x values don't make sense. Well, in this picture, we obviously can't have negative values, so x has to be greater than or equal to 0. It could equal 0. I could put the stake right down at the bottom of that 12-foot pole, so 0 feet away from that 12-foot pole, right at the bottom of it, or greater than 0. But it has to stop somewhere, and it can't go any higher than the 30 feet. It can only be 30 feet away, because then I'll be past my other pole. It could equal that 30 feet. Again, it could be down at the bottom of that 28-foot pole. Okay, so this is my feasible domain. Domain. Okay, but you could also think of as your endpoints. So if I want to find my minimum value, I not only want to check my critical numbers, I also want to check my endpoints. And I want to check those values in my original length of my wire, when x is 0, when x is 9, and when x is 30. And so again, using your calculator, you can find the y value by doing your second trace and value. As long as your first original equation is highlighted, you can find the value, plugging in 0 for x. You should end up getting 53.037. For plugging the value in for x at being 9, you should get 50. And plugging 30 in for x, you should get 60.311. If we're looking for the minimum length of wire, well, the minimum value would be this value right here. Minimum wire length. So I know that the 9 would be the optimal place, 9 feet would be the optimal place to place that stake to use the minimum amount of wire. So I'm going to go ahead and label my answer. I'm going to say 9 feet, but not just 9 feet, but 9 feet where? Well, I know that it needs to be 9 feet from the 12-foot pole, so 9 feet from the left. Okay, if you'd switched the labeling on your picture and you switched the x and the 30 minus x, then you might have gotten something like 21. That's fine, but then you need to do 21 feet from the right. Okay, so just depending on how you labeled your picture. Okay, there's the first example. Hope that helps. Guys, we'll do the second one in a second.